Hi, Dania. We just wait for a couple of other students and then we'll begin.
Hello,
Hi,
good morning,
Dr.
Dr.
Das.
Das.
Right.
Morning. Let me share the screen. Actually, let me uh, upload to let me do something while you guys are there. Let me send a document to you guys. Okay.
Mm.
And for the final project, I'll use this document that I'm just going to send to you guys.
Okay, Dr. Das.
Okay, what I'll do now is I will inbox. Okay. So let me now share the screen. Okay. Okay. Did all of you guys get received my PDF?
Yes.
Yes.
Okay. And are you guys looking at the screen?
Yep.
Okay.
Yeah.
So binary, this is a, just like in homework, sorry, in the exam one, the midterm, I gave you a nice application-oriented problem uh, to implement exactly in the same manner. I just devised a very application-oriented problem in uh, machine learning, which I thought would be an interesting problem for you guys to implement for as part of the take-home problem, take-home questions in the final exam. Now, what we have is, let's see, binary classification. Okay, so we have data of this form. X is a set of inputs or features. Okay, and Y is its category. Okay, Y can be 1 if X belongs to the positive category, and Y must be -1 if X belongs to the negative category. Okay, so there are two categories or two classes, and this is a simple binary classification problem. Given the X, what is Y? Okay, here, for example, let's say you are a credit card company, and here X is the data pertaining to any new application. Some person, his or her credit history, his or her income level, her or age, or I don't know if it's age discrimination or is it allowed, then his or her actually area code turns out to be a very important feature for um, to make a decision, but the problem is it's not allowed by the federal government. Why? Because it's like it divides populations into whites and Asians and blacks and Hispanics and all that. So that's why it's not allowed. I know that for a fact. Anyway, and so the goal is to two classes are approve application if, or deny the application. Given the data X of the applicant, one is Y must be 1 if the credit card company is to approve of the application, or it's negative Y. It's negative otherwise. Okay, so that's a simple classification problem. Okay, and now, so what happens is we want to develop a machine learning problem. Okay, a machine learning model to do a very reliable or accurate classification. Okay, now for this model, we require a lot of training data, training samples. Okay, a lot of previous X's and Y's historically, which is Y is already known if the applicant eventually profited the credit card company or not. Another classification problem could be, let's say, a doctor. Okay, and Y is 1 if the patient has a certain disease, and -1 if the patient doesn't. Okay, in which case X could be all the blood tests, the age, well, I'm diabetic, diabetes, and if the person is vaccinated for COVID, blah, blah, blah. All these are the parameters of the input X for each patient, and Y is +1 if the patient has a certain disease, and -1 if it doesn't. Okay, in this case, the machine learning model that we would like to develop is it will have to use a large data set of previous patients in any hospital, right? Okay, these were the person's parameters, the gender, the age, the blood type, maybe, or maybe the sugar level, the glucose level, or whatever, the cholesterol level of his blood, height, weight, and all that. And Y would be +1s and -1s. Okay, so this is, in this figure, I show you the entire machine learning process. Okay, so what we have is what we need to find is the parameters of this machine learning model. Okay, and they are usually of the form of a set of weights. Okay, so what we need to find, so weights, this W is a vector of weights, and this defines the machine learning model. Okay, like for instance, a neural network. The weights of the neural network, in fact, define the entire neural network. Once you know the weights, given an input X, you can, the neural network can predict the output class Y, which is either +1 or -1. Okay. And so the total number of training samples, let's say, is N, and some of them belong to this positive category, and some of them belong to the negative category. Okay, so during the training process, what we have is XI, a huge database of these sample points, XI. Okay, and then what we do is we find W from this training data. Okay, and here note that what is unknown is W. The labels YI, by labels I'm referring to the Y's, okay, +1 or -1. The labels YI are known. Okay, I is the ith training sample. So XI and YI are given. Okay, and YI here is known, right? This is from historical data, and what is unknown is W, the weight. Okay, so once using this training data, we develop this model iteratively using in this in your test problem, it will be using subgradient. So we find an optimal weight vector W. Okay, and then this weight vector W, we now need to see if it actually works or not, right? So what we do is we keep aside another set of data, training samples, which are not the same as the training data. These are called this is the test data, okay? And then once W has been obtained from the training step, then in the testing step, what we do is we find how accurate the model is given this weight parameter W. Okay, given this weight W, how accurately does the model predict YI from the test samples? Okay, here we're not going to show YI to the machine learning model. We are simply going to input XI's. The weights are now held constant from the previous step, and now we will see if YI that the model predicts is actually the same as the YI that is in the test data or if it's not. Accordingly, we will evaluate the accuracy of our machine learning model. Okay. Now, assuming that the machine learning model passes the accuracy test, then we are good to go. Okay. Now we are ready to use it. Okay. So these weights are fine. And then during actual use deployment, okay, a new patient comes in or a new credit card application comes in, and we have a real input X. Okay, we actually don't know what the Y is. We're going to guess the Y. And using this W, we try to predict Y. What's the Y? The label corresponding to this input vector X. Okay, any questions?
So you said that the X could have a number of parameters to it. Is the weight only going to pick out a certain combination for X, or can it be a collection of different combinations for the parameters of X?
Can you repeat that question? Sorry, I was actually testing if I'm taping, recording this lecture or not. And
Oh, okay.
sorry, so
No, it's okay. So you said that X could be any collection of parameters, so like Xn. So the weight vector, is that usually determined on one specific combination of X, or are there a collection of combinations the parameters could be for Y to be categorized as like positive or negative?
it's always a vector, a collection. By a collection, you mean like different different parameters of the input, different
Yeah.
fields of the input, right?
Yeah.
It'll always be multiple. It's a vector always.
Okay. And then so for all those different X, the weight isn't just on one set of
The
this.
weight will be all based on, so it's based on all of these. Not only, we don't have a separate weight yi, sorry, excuse me, wi for each xi and yi. It's the same weight w.
Okay.
Okay.
Yeah. Thank you.
It's just one model. We do, like, if we have a different model for each of these, then which one are we going to use, put into use during actual deployment, right?
Yeah, that makes sense. Okay.
So we just have one machine learning model, and given any xi, we train it so that it gives the right yi from the training samples, which is known. Then we evaluate the performance using test data, and then if it passes the test, the performance metrics of the machine learning model or classifier model, as I've written here, is good enough, then it's ready for deployment. Given any x, now weight is fixed. Given any x, we try to predict. Okay.
Okay.
For instance, a doctor can uh, instead of actually thinking and diagnosing what the patient is, he can simply refer to, he or she can just use this model and then say, okay, you have this disease, or you don't, you probably have this disease, or you probably don't have this disease. Okay. And these are all the database, the training and data is a huge database of all the doctors, previous patients, and their outcomes. YI is known. Okay, but this, and here we develop this weight W, which consists of the parameters of the classifier model, the weight, and it's fixed for, like it's the same W for all of these. And then with another test data, this W is now fixed, okay, and known, and we see if the yi being predicted is the same as the yi. Sorry about that. I'm so sorry. distributed. So is the problem clear to you now?
Yeah, thank you.
So now, given any point xi, we call this a feature usually. I equals 1 through n, and we denote the label yi. So the training data is this set D. D equals xi yi, where I equals 1 through n. Okay. Now, we want to find a W, right? So we are in the training process. We want to find the W, given this training data set D. Okay, so what we should do is let the optimal weight vector be denoted as W star. Okay, so we should find this. What is this is our objective function to maximize the probability of the. Now we have a probability distribution of the weights. Maybe it's Gaussian, maybe it can be any Bernoulli, it can be any distribution, right? So we have some, okay, this is given, if this is the data, this is the most likely set of weights. This is the probability that the weight vector is W, okay? And so what we want to do is we want to maximize the probability of W given the set of data. And this is this uppercase phi of W. This should be our objective function to maximize. Do you guys agree?
Yes.
So this is the probability of W. So the probability of W being equal to some value given the data set is maybe 0.2. The probability of W being some other value given the data maybe 0.3. Another for some other value of W, the probability is 0.9. Okay, so which W are you going to put? Okay, so what I'm saying is, suppose you have multiple options. Okay, suppose we have to choose between 3 different values. Okay. We have 3 choices for W, just hypothetically. P of W, we have W1, and let's say this is 0.3. Then we have another weight vector, P of W2 given D is, let's say, 0.4. And we have another one, W3, for which this probability is 0.9. Okay, now suppose these are the only 3 possible choices of W. Which one will you pick?
W3.
Yeah, 0.9.
W3, right? Because it has the highest probability, correct? So that's what we want to maximize, the probability of W given the data D. Okay, but let's apply Bayes' rule. From Bayes' rule, the conditional probability of W given D is equal to the conditional probability of D given W times probability of W divided by probability of P. Okay, now this is a conditional probability. Probability of the weight given the data. This is probability of the data given the weight. This is the probability of the weight. So this is a prior probability. This probability is independent of the database. Okay, note this point. This W is independent of D, the database, training samples, and then divided by the probability of D. Agreed? This is Bayes' rule. Now, this P of D is independent of W. Okay, so it doesn't have W in it, right? So we can simply ignore this. What's the probability of this data? Well, we already have the data, right? What's the probability that the patients of the doctor in the past 5 years were this training data? Well, we don't need it because we don't use it. It's independent of W. This is actual real data, and yi's are the actual values, right? So we can ignore this denominator P of D. Whence our objective function can be simply PD given W times P of W. Okay? Are you guys okay so far?
Yes.
Yeah.
And I remember we had done something like this earlier in one of in section A of this course. I don't remember exactly where, but we did. Do you guys remember? Anyway, so this is what we could maximize then. We would like to find W that would maximize this objective function, uppercase phi of W, which is probability of the data given W times the probability of W, the prior probability of W. This is called the prior probability because it's prior to the data, what is the probability of W? Okay, so this is called the prior probability, or simply the prior of W, and this is called the likelihood. P of D given W is called the likelihood of W. Okay, so this is what we want to maximize. However, we choose to take the logarithm for reasons that will be clear in an instance. So what we want to do is we want to maximize the log of this function. So lowercase P of W equals, and now the product becomes, when you take the logarithm, it becomes what? A sum, right? So P of W is log log of the product, this dW times this, which is equal to log of PD given W plus log P of W. Are you guys with me? So we have two terms in the objective function that we want to maximize. This is our objective function. Okay. Now, this L of W is the first term here. I told you is the log of the likelihood. So we call it the log likelihood function. LW equals log P of the data given W. Okay, and the second term, this is log of the prior. Okay, prior probability of W, which is independent of D. So we define that as our regularizing term, and that's log P of W, log of the prior probability of W. Whence our objective function W equals the log likelihood plus the regularization. Whence argmax of this W star equals argmax with respect to W of LW plus RW. Okay, are you guys clear so far?
Yep.
Yes,
Yep.
Dr. Dr. Alvan, and the maximum is the same with that log?
Here, here.
How when we apply log,
Yeah.
we have the same
The
maximum?
maximum of the function, the value of W which maximizes the function is the same as the value of W which maximize the log of the function, because the log function is monotonically increasing,
Okay. Mhm.
right? So this is what we want to maximize. Okay, now let's actually do the maximization. Let's find what this log likelihood of W looks like, and then we'll find what this regularizing term RW looks like. Okay. And according to the logistic, let me call it logistic regression. There's one very common approach in machine learning and statistics called logistic regression. Okay. Now, what we assume is, suppose W is the weight. Okay. Then log of the ratio, so there's a certain probability that Y equals 1. So this is, we are looking at probability of X, probability of Y given X and W. Okay, so suppose W is fixed and X is provided. What's the probability of Y being equal to +1, and what's the probability of Y being equal to -1, right? Now, we make this assumption that the log of the ratio of the two probabilities is W transpose X. Log of probability Y equals +1 given X and W divided by probability of Y equals -1 given X and W. And the ratio of these probabilities is equal to W transpose X. This is the assumption that we make in logistic regression. Okay, and here you see W. Now, from probability theory, the probability that Y equals +1 given X and W plus the probability that Y equals -1 given X and W equals 1, right? Either it's +1 or it's -1, nothing else, right? So the sum of the two probabilities, Y equals +1 and Y equals -1, must always add up to 1, right? And if this is a log of the ratios, then what is the ratios? I take the inverse log on both sides. This would be equal to e to the power of W transpose X, right?
Yes.
So once we use these from these two expressions here, this expression and this expression, it's very easy. You can derive this expression. Now, this Y can be +1 or -1. Okay, right? So I'm using just Y here. The probability of Y equals +1, that this Y is +1, is e to the Y is +1, right? So e to the W transpose X divided by 1 plus e to the power of W transpose X. And the probability of Y equals -1 will be e to the power of, here, now you have to put a negative here because Y is -1, e to the power of minus W transpose X divided by 1 plus e to the power of minus W transpose X. Okay. So this is shorthand for this. Probability of Y equals +1 being this is this, and the probability that Y is -1 is this. And you can easily show that the sum of the two probabilities must add up to 1, right? This can be easily shown. Okay, this And it can also be shown that the ratio of the two, y equals cross 1 is this. So this divided by this equals or log of this log of this now this becomes minus, right? Minus log of this should be equal to W transpose X. Okay, so these two expressions can easily be shown to be true. And you can verify this. Are you guys all clear?
Yeah.
Yes.
So now this probability of, we want probability of D given W. Okay. So probability of, consider just, so this is the probability of the, which is log of, okay, so this is, sorry, I got this expression for each sample point, yi and xi, we would get this as a probability, right? Pyi given xiw is equal to this. Okay, I should have, maybe I can rewrite this in a, so that it's clear to you. I'll rewrite this portion. Okay, so for any sample point xi, yi, this is our probability. Probability of yi given xi and w is this. Correct? Agreed?
Yes.
And
Yes.
what is probability of xi comma yi given w equals, from Bayes' rule again, this is equal to this correct?
Yes.
Now, we are trying to devise something, the log likelihood function, okay, using this logistic regression. Now, this P of yi is independent of w because xi yi is a input sample, a training sample that's given to us, correct? So now the log likelihood function of this is, and so this is equal to this. Correct?
Yes.
Yep.
So what's the probability of the whole data D given W? It's equal to the product, oops, product of this, right? All of these. I belongs to D, correct? probability of sample 1 times the probability of sample 2 times the probability of, this is what I'm trying to do. First sample times probability of the second sample and probability of the last sample, the uppercase nth sample.
Is this still using Bayes' rule?
No, this is the product of so joint probability.
Okay, I got no. Sorry.
Okay, so this is the joint probability of the entire data, all the samples, which is equal to, I'm expressing it conveniently as this. Okay, so the log likelihood is basically the log of this. Agreed? We define the log likelihood as the log of probability of the training samples given W. Agreed? So this,
Yes.
what I do here is I take the log of this. Why do I take the log of this? Because this product of all these factors, once you take the log, it reduces to a summation. Okay. Are you guys good?
Yes.
Yep.
So now this, what about this term? This is the probability of yi. Let's say we are looking at patients. So this is the probability of yi, and this is historical data, so it's independent of W. This entire term is independent of W, right? And so we can just ignore this part. And hence, since we want to maximize, we can just ignore this part. Hence, we take this as our log likelihood function, LW. This. And when you take the log, this product of all these factors now reduces to a summation. Okay? So this log of the product of all these terms now becomes a summation. Summation, and in 2 steps you get this. So now summation of the log of e to the yi w transpose xi, which is equal to log of e to the something is that something itself. So this minus, so division becomes minus log of the denominator here. Okay? Are you guys okay with this?
Yes.
Yep.
Okay, so now L of W is this. This is the expression that we will use for L of W. Okay. And since we are eventually going to use a gradient-based approach to find the optimal value of W, we need its gradient. So taking the derivative of this, we get differentiating with respect to W, we get this first term is simply yixi. I've taken xi common, and the derivative of the second term is this times xi. Okay. and which is equal to, now this is actually probability of yi given xi. So this is the final del of this. If we use this as the log likelihood, then its derivative is this. Okay, and that's what we will use for when we do this, when we want to find this W. This is the training step. Okay. Are you guys all okay so far?
Yes.
Yep.
Now, what's our next step? So this is the objective function that we want to maximize. This is L of W, the log likelihood, and we just derived this expression for the log likelihood. The regularizing term is what? Log of the probability of W. Okay. Now, which is more likely? Suppose, let's say, any scalar component of the weight W. Okay. W, any scalar component, W is 10,000 or W is 1. Which do you think is more likely?
W is 1.
Yeah. The lower the value, the likelier is the weight. And it's kind of common sense, although there are more formal reasons behind it. Okay. So we want the bigger the value of W, the less likely it becomes. So this is our assumption. The probability of W, the prior probability of W is e to the power of negative beta for some beta of the one norm of W. So which has the highest probability? W equals a vector of all zeros, right? This will have the highest probability. Actually, there would be some constant k here, but I'll ignore that constant. So this P of W is some, let's call that constant C. Okay. So this is the Laplacian distribution. So we assume that the probability of W follows this Laplacian distribution, centered around the origin 0. Okay. Whence log P of W equals this. You see this, we have negative beta times the one norm of W, and then plus log of C, but log of C is some constant independent of W. Okay, so we can simply ignore the second term. And so this is log P of W. Negative beta times the one norm of W. Okay, and we use this as our regularizing term. So negative beta times the L1 norm of W. This log P of W. This is the regularizing term, R of W. And that's what we use for where were we? For regularization. Whence this is our objective function. P of W equals L of W, which we have devised here, minus plus R of W, and R of W is negative beta times L1 norm of W. So this is our objective function that we want to minimize, which is also equal to this. Okay. Are we good?
Yeah.
Yes.
Okay. So now this L of W, we already have an expression for its derivative. Okay. But this one norm is not differentiable. Okay. So its gradient, now let's consider this del of this with respect to W, del of the objective function will have, it'll be a vector, right? One for each scalar component of W. Consider the jth scalar component. Okay. So the jth scalar component of the subgradient of this will be the gradient of this with respect to Wj minus what is the derivative of beta times the L1 norm. What is the L1 norm? L1 norm is nothing but the summation of the absolute values of the weights, right?
Yes.
Yes.
So this, I can write down, so this is what I'm saying. This is equal to summation I or summation J. I'm using J as my index here of the absolute values of this. Right? This is what I have, right? This is the definition of the L1 norm. So how do you differentiate this with respect to any Wj? Actually, let me write negative beta here. The regularization term is negative beta, which is equal to negative beta times this summation. Okay. Agree? What's
Yeah.
the subgradient of this? If Wj is strictly positive, then absolute value of Wj is equal to Wj, right?
Yes.
And when Wj is strictly negative, the derivative of this with respect to Wj is negative of this, right? Correct?
Yes.
Okay. So this is, and when this Wj is exactly zero, then what is the subgradient? Subdifferential is anything between +1 and -1. We've seen that earlier, right?
Yes.
Hence, from this, we get this as our, when Wj is less than 0, when Wj is greater than 0, and when Wj is equal to 0, the subgradient Gj is anything between this and this. Okay. And so I have explained this, and this is the gradient or the subgradient. what we do is, in fact, when Wj equals 0, we simply choose 0, which is exactly between negative beta and plus beta, to be the subgradient. Okay, so the derivative of the L1 norm of W is simply defined is the sine of W, where the sine function is sine of W is negative 1 when W is less than 0, 0 when W is equal to 0, and plus 1 when W is greater than 0. And this is the expression for the subgradient of the loss function. Are you guys good with this?
Yes.
Yes.
Okay.
Yeah.
Now I know someone has to leave at 11:30. One of you guys has to leave at 11:30. Am I right? Anyway, I'll rewrite portions of this so that it's better explained. But what I'll do is I'll give you partial code for this, and I'll give you training data. And then what I'll do is I'll also give you test data so that you'll be able to evaluate how good is the weight that you obtain from gradient descent, subgradient descent. Subgradient hasn't really, because you want to maximize the function. Okay. And I think this is a very interesting homework. Actually, exam problem. I'll give you a little more time for, to absorb this and do it. And the other thing is, the last lecture, lecture 9, B9, I've dropped that from the curriculum so that we don't, you don't have to study Newton's method and the penalty function and augmented Lagrangian methods. It's good if you know that, but I'm not going to have new questions. These are algorithms, and I think just applying this is good enough for you guys. Okay?
Yes.
Okay. So do you guys have any questions about this first, or in general, any other questions?
When is it going to be the final exam and the take home?
I think it's going to be 9th or something is the Monday, but you can submit the I'll check 9th, so you can submit it on the 9th. This one, I'll give you the take-home portion, and the quiz 9, or you can actually submit it later than the 9th. I'll check. Okay, you can submit it the last day of the exam. I think the end of that week, exam week, you can turn it in. And the quiz, we have to think now. Officially, the quiz has to be held during the actual exam time, which is I think 9 a.m. or something. But for the off-campus students, that's not possible. So I'll think what to do, and I'll let you know. It'll be this weekend. I'll let you know. Okay.
Okay.
So any other questions?
For homework B2, the one that we have, it was, yeah, B1 or B2. B2, homework B2. Yeah. Do we need to change any parameters to get better result, or we just keep what you already?
I don't remember what it was. This, right?
We don't see it. We see the Word document.
Oh, this one, right?
Yes.
Well, it could, I know it could give some better results with some other value, but it's okay if you use that value. In fact, it's easier for me to check if you use
Okay.
that same value.
Okay, thank you.
And because time is short, it's out of 10 only. And so but you get 10 points bonus. And to that, I'll read this out of 10 and I'll that so that you get some score out of 20.
Okay, thank you.
You get 10 if you don't submit anything. Any other question?
I had a question from homework B1. It said something about symmetry for question 3 and for the solution. And I was just wondering if the symmetry came from figuring out that x1 equals x2 equals x3, or if there was something from the problem.
No, x1 equals x2 equals x3. Yeah.
Okay, that's all that's symmetry.
That's all.
Okay,
Without using symmetry, you can still solve it, right?
right. Okay. Thank you.
About homework B1.
Hang on.
Yeah, B1. And question number 5. How do we implement that using MATLAB? How do we implement the A and B?
Question number
5.
It's the F-min con. Well, F-min F not F-min con. What's the MATLAB command? F-min opt or F-min unc UNC.
Sorry?
F-min UNC. I think that's the one for unconstrained optimization.
Okay.
Or you can use F-min con and give, it's your choice. You can, yeah, it's F-min unc. You can use F-min con and just pass null vectors as A, B, A equal, B equal.
Okay.
Which approach did you guys use? For those of you who did it, I don't remember.
Main con.
F-min con, okay. So this is, I mean, it's trivial, right? You use F-min con. It's your choice. You can use F-min opt too. Sorry, F-min unc too. So any other questions? Homework B1, homework B2, or any of the rest of the course material? Okay, so we conclude today's session then. So in the quiz, I'll ask you very simple questions about the KKT conditions, and duals and all the graphical stuff is important. You have to understand all the graphical interpretations. And I'll have some theory questions and MATLAB for the take-home portion of your exam. Okay.
The take home will be only the MATLAB code.
No, no, no. I said theory portions and some of this MATLAB. Okay.
Yes, we are going to have lecture this Tuesday.
No.
No, okay.
So no more lectures. We're done. Okay. See you guys then.
Thank you.
Thank you, Dr. Dawes.
Okay.
Thank you.
Take care now.